All right. Now, this is kind of like, I didn't put any mu's in, but just like we did before, we can always put the mu's in. So if we put the mu's in, everybody gets a mu. The h is like the mu of the Wilson coefficient, and then the j's are like, and s's are like mu's of, from the point of view of SET, they're like mu's of the operator. And we're just switching to renormalized operators and renormalized Wilson coefficients. Now if we draw our scale diagram again, but draw it a little bigger this time, and put in where these various functions are. So somebody was blue. Not going to label everybody again. So this is the hard function. Our jet functions are kind of sitting at this scale. They had to do with the collinear modes. And then our soft function is sitting at this scale, or this and this scale. So it's clear that these things sit at different scales. And what that means from the point of view of the formula is that if you associate what scale these things want to live at, which from the point of view of perturbation theory means at what scale would I be able to calculate these things, given that they're perturbative? Would I be able to calculate these things without encountering large logarithms? And that would be these scales that I'm writing here. So these are the scales where we could do perturbation theory for the functions without encountering large logarithms. So we can figure out what these scales are by just looking at the perturbation theory and looking at the logarithms. But you see that it's a different scale for each of the different functions. So in this formula, there's a common mu, which is like a factorization scale. But each of the functions wants to live at a different mu, and we're going to have to do some renormalization group evolution to put things at the at the scales they want to be at, and then there'll be some resummation going on, and that's going to sum logs of m squared over q squared. So we need a normalization group, and that's going to sum up logarithms, which are ratios of these scales, which expressed in terms of some physical thing is, in this case, logs of m squared over q squared. All right. What about this situation here? Well, it turns out, and I won't go into it in too much detail, but we can factor that guy. If these two are hierarchical, we can actually factor this in something called the soft function OPE. And even if they're not hierarchical, we can actually write it in the following way. So we can always, in some sense, whether or not we're in a situation where these are comparable or whether they're hierarchical, we can always use the following formula. We're not guaranteed that that is possible. But in this situation, it is possible to sort of make those two situations compatible with each other with a single formula. Usually when you design effective theories, you kind of, for each different expansion, you have a different result. And making them, whether you can put them together into a single result is not always guaranteed. But this is a situation where we can put things together in a single result, where these are the perturbative part of the soft function. And this is the non-perturbative lambda QCD effects. If you imagine that the function, if you imagine that these two x's are hierarchical, then this perturbative guy here gives you some alpha s corrections. And it basically, in terms of the L plus, in terms of the momentum variable in this formula, it's giving something that's like what's called a power law tail. So the kind of dependence that you're getting is some logs over an L plus. And that's called the power law, since it goes like 1 over L plus. Whereas these effects here that are non-perturbative live down at non-perturbative momenta, and you can actually prove that they have an exponential tail. So this is some plot of f in a one-dimensional projection. So let's just think of it. It's one, and this is some scale of order lambda QCD. So it's some blob down at lambda QCD that's describing the distribution of soft hadrons. And it's non-perturbative. It's not like I'm drawing it because I know it, right? So it looks something like this. Whereas this part we can calculate, and it has a different dependence. This is a power law. This is an exponential. OK, so that's like kind of further factorization of the S to make those two x's separated. Could separate the perturbative and non-perturbative corrections. In some sense, if you're in a situation where they're comparable, then whether you take a non-perturbative function, and if L plus is small, and you integrate it against this, you're just getting back some other non-perturbative function. So this formula is not really, there are some things that this formula is actually doing even in that situation. It's ensuring that you're in the MS bar scheme, for example. But the sort of more important in some ways is when they're hierarchical, and then you can start to expand this thing, and because in that case, this L plus prime would be localized down here, and the L plus, if the L plus got big, then you could start doing a Taylor series, and this formula would tell you how to put the corrections together. Okay, so there's kind of a lot of physics in that formula that I'm not going into in detail. Yeah.
So, I don't know that I entirely understand why this is valid. Are you allowed to? Does the soft function encode all modes like below that hyperbola?
Right.
Is that
That's
true?
right. Yeah. So below the above one, and
below the S one. Yeah.
That's right. That's right. The soft function. You should always think of these things as kind of extending down to the axes, right? In some kind of fashion. So let's draw it like this. Since they're infrared modes, and the infrared is sort of down at the axis, you should always think of them as extending down to the axis. Now, exactly how you want to think about how the soft modes whether the soft modes are capturing the entire axis, or the collinear, how the collinear modes and the soft modes, kind of what the edges are, is related to the power counting. And you can think of the collinear modes as kind of being held away from the axis because the soft modes are really deeper in the infrared. But
at higher power, are you going to scale these up if you say, like, suppose the soft modes have a invariant mass of lambda to the fifth, right? Or they're smaller than lambda to the fourth.
You never have to worry about, you could worry about putting in more hyperbolas, right, with lambda QCD over Q or something.
Yeah.
And you don't have to do that.
Okay, so
you never have to do that.
Yeah. Why is that?
I mean, essentially that's because any lambda QCDs, what this X means is that lambda QCD is encoded in this kind of non-perturbative soft mode. And if you had something that, at higher power is like lambda QCD, to take your example, to the sixth, the 1 over Q to the sixth is going to come out in some coefficient. And the lambda QCD to the sixth is just going to be some matrix element of this mode that has that dimension. That's how it's going to work. So in some sense, you could say, well, what if I put a mode down there? And I would just say, well, that mode's inside this mode. You don't have to write down something different for that. It's all encoded in the Lagrangian for that mode. I mean, that mode has all the non-perturbative physics.
Yeah, just at a higher power, I would think
Yeah,
if
no.
you're comparing
So
You're
this is
comparing 2 powers of
this is a
linear
good
with 1
question.
power of solid,
Right.
and the solid
So
is actually secretly much smaller.
yeah. So one way of thinking about it is like this. When you design the effective theory, you actually have to figure out what the degrees of freedom are at lowest order. And when you go to higher order, you shouldn't be having new degrees of freedom popping up at you. Yeah. And so that's kind of at the heart of what I'm saying here. That's a kind of an even deeper way of saying it. Because what you're doing with the power corrections is you're kind of figuring out how to put factors in the numerator if you want to think in Feynman diagrams. You're not changing the propagators. You've already figured out the propagators with your leading order theory. So you have sort of where all the poles can occur, and now you're just sort of doing perturbation theory. Perturbation theory shouldn't introduce new degrees of freedom kind of in the power when you're expanding in the power expansion. All right, so to draw a picture, I want to tell you about one other observable, which is thrust. So thrust can be defined by this formula here in general, which is that you find some axis, which is actually an axis that's going to, in our Dijet configuration, be the jet axis. You find the axis that maximizes this thing, and in the case of a Dijet configuration, that's going to align with the jet axis. And then you do this sum, and that calculates some variable t. T turns out to have kinematic limits between 1/2 and 1. And if you want to talk about something that's a little more convenient, you define something called tau, which is 1 minus t. And the Dijet limit of tau is 0. That's why this is more. So the Dijet limit of t is the limit where you would just have kind of two pencil-like back-to-back things. In that case, this goes to 1. And if you want to define something that goes to 0, then you define this tau, which is a little more convenient. And so it's possible to work out that when you're in a Dijet configuration, that this tau, with a bit of work, you can show it's actually simply the sum of our two hemisphere invariant masses. So obviously in a Dijet configuration, there's lots of simplifications to the kinematics. And with some work, one can show that that's true. So what this is an observable which is simply a symmetric projection of our previous two-variable observable onto one-variable observable. But if we demand that, for example, tau is small, that's demanding both m squared and m bar squared are small because they're positive quantities and we're just summing. So demanding that this is small is demanding both of those variables is small. So tau much less than 1 also is a way of getting Dijets. And that's a way of getting Dijets just with one variable rather than two. So that's, of course, easier to draw a picture with one thing rather than two. So if we take our formula for the two variables and we project onto one, then we can do that. It looks like this. So what happens to the two jet functions and the soft function that had two variables is that they get projected kind of onto their symmetric projection of the two variables. So this is like these two are like symmetric projections. So we had two variables before, and now we have one variable, and it's like a symmetric projection, and that just follows from this formula. So literally, to get this result, we would just do the same trick we did before. We'd say, that this is true. Now let's move the integral dm squared and dm bar squared onto the right-hand side and think about doing those integrals, and we'd follow through, and it would lead to a formula like this one.
J tau is like j squared.
J tau is j squared. J tau is literally j integrated over, so fixing the kind of the sum of the momentum and integrating over the difference. Okay, so this guy depends on one momentum, and these guys depended on two, and there's one integral. And then S tau is like one integral of kind of something like this. So that's called the integral L prime. It's kind of like that. So that's what I mean by symmetric projection.
And suddenly in power, do you know that tau can be written as a function in n and n bar? Or could another kinematic variable come out?
You know it can be written as a function of n and n bar. Yeah. Because you're still, if you're in subleading power, as long as you're in the Dijet configuration, we've got the right degrees of freedom. We don't need another jet degree of freedom. Yeah. So if you want to describe, you could think about the thrust distribution. Well, let me answer your question in more detail. Let me tell you where you would have to worry about more degrees of freedom. But let me do it in a second. I'll give you All right, so in the thrust case, kind of what we said about masses carries over to a formula like this, where this is UH squared being much bigger than mu j squared, much bigger than mu s squared, and then that could be much greater than or of order lambda QCD squared. And the type of terms that our factorization theorem would be able to resum if we did the renormalization group evolution would be sums of powers of alpha and logs of tau. Tau is a dimensionless variable, and so the kind of terms that would show up in the cross-section are terms like that, plus non-perturbative effects. So if you want to think at a base level what is inside our formula, it's all these terms. We're able to determine them from our factorization theorem. And then there's also some non-perturbative, really it should be kind of, and non-perturbative effects that are in this f function. And the factorization theorem is telling us how to compute these things and include them. So what does it look like as a picture? What does the cross-section look like? So there's a peak, as I promised. And then there's a tail. And so this is a tau. This is d sigma d tau, which you can always normalize. This peak is happening in the kind of non-perturbative region, so because it's a symmetric projection, there's a factor of 2, but it's kind of basically happening when tau is of order lambda QCD over Q. And we could figure out that just by power counting. And then, depending on the value of Q, but sort of for a typical configuration, tau equals 0.1 would be over somewhere over there, et cetera. So this is the peak, aptly named because it looks like a peak. And in this peak, there's non-perturbative effects that come through the F. This is the tail. It could be called the shoulder, but it's kind of, once you're out here and down here, this is what you call the tail, where you have a perturbative S tau, and then you would include power corrections by expanding. And the expansion would give you lambda QCD over the soft scale, which is Q tau. Okay, so this is that's that expansion that we talked about. And that comes from expanding it F, where it's an expansion that involves F. It's not expanding F. It's basically what these numerators are moments of F once you do the expansion. And then there's a region out here, and in both of these regions you have dijets. But in this region out here, you don't have dijets anymore. That's where tau is starting to get large, and you no longer have dijets. So if you wanted to think about sort of higher order corrections in the distribution out here, then you would need to perhaps think about 3 jets and other things. In particular, there's also like a kind of shoulder here that if you really want to think about how power corrections are kind of properly dealing with that region, you should think about kind of more than 2 jets. But if you just kind of restrict yourself to here and here, which is all we're going to do, then every mode, even if you go to subleading order, is exactly the ones that we just said, and you just have to deal with them by constructing operators in subleading order. So that's the more detailed answer to your question. Any other questions?